Hello guys, welcome again to this video. So from this video onwards we would be trying to prove and continue our double integral which we had evaluated in the last one. So let me just give a quick recap of what we have done in the last video. So this was our double integral which we intended to find, and we had made some progress on it. The progress specifically was to group the terms and make a substitution of u equals to x by y, which eventually gave us the form that is, let me write it down. So when we make the substitution, u equals to x by y, keeping y fixed, we have du equals to dx by y, and the integral turns into something like this. Y equals to 0 to y equals to infinity e to the power minus y, and inside we have u equals to 0 to u equals to infinity e to the power minus uy u to the power s minus 1 du, and then there is a dy, right? So this is where we reached in the last video, and we would like to continue it from here. And obviously in doing so we would be trying to understand how do we basically evaluate this particular integral right here, which is the modified form of the initial integral that we started with. But then again, what we are going to do here is basically we are going to switch the integrations. So we are going to switch the order of integrations, from which it will appear that we can do u equals to 0 to u equals to infinity, take the u thing, the things which only consider of u outside, and inside we can evaluate the y integral first as follows: y equals to 0 to y equals to infinity, e to the power minus y is common, 1 plus u dy, and then there will be a du. Now this is an easier integral to evaluate because of the fact that e to the power minus ax for integral of x from 0 to infinity is just 1 by x, right? So this integral is a rather simple one. Let me just do it. Understand that u is a constant in this integral because it's just a variable y, so it will be 0 to infinity u to the power s minus 1, and inside it will be e to the power minus y into 1 plus u by 1 plus u. There would be a minus here, and it would be from 0 to infinity du. So evaluating it at both points, you see that when you put in the infinity it becomes 0, and when you put in the 0 it becomes 1, and since there is a minus sign, that would be a plus 1. So ultimately what it would turn out is as follows: 0 to positive infinity u to the power s minus 1 by 1 plus u du for 0 less than s less than 1. Therefore, from this whole operation, what we have concluded is that that gamma of s into gamma of 1 minus s is basically 0 to infinity u to the power s minus 1 divided by 1 plus u. So this is basically how we evaluate this integrals. But then this integral again here is something we need to evaluate using complex analysis, and this would be a little bit of a tougher job to follow than the previous ones. But then I will just show you a whisker of how to do this, because you see in complex analysis when we do contour integration, this thing often comes in the mind, and we see that u to the power s minus 1 by 1 plus u is a integral which can only be evaluated using contour integration. So this is basically how it works, and well, there are three proofs basically that we can understand from here. The first proof here would be to use the contour integration fact. So let me just write it down. Okay, so let's do this part first. Let I equals to 0 to infinity u to the power s minus 1 by 1 plus u du, and as you can see, this integral may well be represented in terms of a integral which you can represent in the complex plane, because you see that whenever you have a polynomial equation or a standard polynomial equation where you are trying to find out the poles of it or something like that, what you do usually is this. So what you try to find is you see that when you have an integral like this, pz by qz, where z are the complex numbers basically, what you try to do is you find the poles of this function. Poles are the points where you have q of z equals to 0, and this poles will represent, so q of z equals to 0, these roots are called poles of p of z by q of z. Okay, so the points at which this function is not defined is called the poles. That is how it works, and whenever you have such an integral here, you can do that. But then again, in this particular case, what we do know is that minus infinity to 0 u to the power s minus 1 by 1 plus u is something that we cannot evaluate directly. So rather what we do here is use the analytical continuation of the gamma function, where we basically find out how to do this. So we know that the gamma function can be found out as follows. This is a representation that is used for gamma z inverse that is used by Weierstrass first, and this can be represented as z into e to the power gamma z and summation n not equals to 0 e to the power 1 plus z by n exponential of minus z by n. So this is how the gamma function works, where this gamma thing, this is called the Euler's constant, or you can call Euler Mascheroni constant. Its value is somewhere around 0.5772 or something like that, and it is defined as a infinite limit, which is this limit n tends to infinity hn minus log n, where hn is the harmonic number or sum of the reciprocals of the first n natural numbers. So yes, it is a very complex thing, that is why I am not going to get into it, but this gamma z inverse has a Weierstrass product representation which we shall use in order to find all these numbers. So it is this product is taken over all positive and negative integers except for n equals to 0. So that is how you find this gamma function here, but well, that is out of our topic for now. What we are going to do is to accept this as a fact that this integral right here, whenever you see an integral of this kind 1 plus u du, you can directly write it as gamma of s into gamma of 1 minus s. Later on, when we introduce the beta function, this kind of integrals become even more simpler, because then we can use our own functions here. Then we can use it and represent it as a beta function. In fact, this here right is also a beta function, which we shall see. So that would be it for this video. In the next video we shall see and introduce some more properties, and we would try to make sure that we understand the beta function in the next video by introducing it and then giving a proof of it. So for then it will be I hope you like the video. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.